it's very dangerous to start a talk by contradicting Einstein. But I'm going to do that because here I'm not interested in this phenomenon or that phenomenon. I want to know God's thoughts. The rest is mere detail. Now, most physicists wouldn't agree with that. I mean, of course, one does want to know fundamental laws of physics, but one also wants to explain things. And in fact, Einstein didn't really adhere wholeheartedly to this maxim. He co-designed a type of refrigerator. He wrote a paper on the meandering of rivers. Okay. But against this is Robert Hooke. The truth is, the science of nature has been already too long made only a work of the brain and the fancy. It's now high time it should return to the plainness and soundness of observations on material and obvious things. Well, they're both right and they're both wrong. But I am going to speak about one thing, one phenomenon, namely tidal bores. Now, it's a wave that travels upriver. How many of you have seen it? Oh, wonderful, wonderful, good. Travels upriver. Oops, where am I? Yeah, here's one in Brazil on the Pororoca, a tributary of the Amazon. Here's the tide flowing in and the river is flowing downstream. Here's ours, our local one, and here it is again. And you see the scale of it from the surface. Here it is again. And here's on the River Nith, a pretty little bore, the River Nith, which is near Dumfries in Scotland. And here it is again. And well, here we are. I don't need to explain this map. The bore takes place on the River Severn. There's Gloucester, zooming in and zooming in again and magnifying this. This is where the bore occurs. It starts actually a little bit downstream of here and it ends at Maysmore. It used to go all the way to Worcester, but there's a weir just beyond Maysmore that stops it. Good. Now, it's a tidal phenomenon. And the first thing to understand is the tides. And people are often puzzled by the fact there are 2 tides a day. The moon is on one side, it pulls the water. So why isn't there only 1 tide a day? Well, there's beautiful physics in that. You see, the force on the moon side, water, is greater than the force on the solid earth. And the force on the far side, water, is less than the force on the solid earth because that's farther from the moon. Now, the earth is free to move. It moves, whoops, excuse me. It's falling freely in the gravitational field of the sun, mostly, and the moon a little, the solid earth. And that falling freely is something, well, Newton sort of understood it, but Einstein really understood it. It's called the principle of equivalence. It's related to the indistinguishability of acceleration and gravity. I mention it because, I've known this for decades and teach it and so on, but I discovered a beautiful anticipation of it many hundreds of years ago in the Arabian Nights. So let me just read this to you from the Arabian Nights. The bird rose and rose, this is with Sinbad, until I thought I was about to touch the vault of heaven. Then suddenly it dropped so swiftly that I could not feel my own weight. That's exactly the principle of equivalence. So what's relevant is not the force on the earth, but the difference between the force on the water and the force on the earth. And that's, if you work that out, is outwards, both fore and aft. So there are 2 tidal bulges, and as the earth goes round, underneath these 2 tidal bulges, you pass one of them and then the other one, so 2 tides a day. Now, the other point is, well, the gravity from the sun is much greater. So why is it the moon that dominates the tides? The answer is actually it's the same. The difference of force, let me be mathematical for a second, instead of an inverse square, it's an inverse cube. And that difference of force is dominated by the moon. It's an inverse cube force, but how can I get rid of this thing? Oh, I hate it. It's an inverse cube force, but what that means actually is that the sun tide is not dominant. It's about half as big as the moon tide. So the tides vary a lot depending on whether the sun and moon are in line and various other astronomical alignments. I want to get rid of this thing and I don't know how to. How can I get rid of this? You can show me. I don't want it to contaminate. There's something to do. It's a view thing. It's one of those.
See what we get here.
If you can't get rid of it, I'll continue, but one should be able to.
Well, it should be tide float meeting controls.
Never mind. Oh yes, bless you. Good.
So far, so good. Oh, you all right?
Good, yes. Okay, well that's the first thing, 2 tides a day. Now what about bores? Well, a bore is it's the tide coming in as a wave. Now, waves on the seashore, they're different. They're caused by the wind, and they're small, I mean a few meters long. The tide is a wave that goes halfway around the earth. It's a huge wave. But why do waves break as they go into shallow water? Because this happens with the bore. It's the tide wave gently shallowing and narrowing and through as it travels along an estuary. Well, oops, here we are. So this is how it happens. These are ordinary waves on the seashore. Why do they break? They break because the speed of water, waves on water, increases with the depth. It's actually the square root of the depth. It gets bigger. Now, the crest of a wave is in deeper water than the trough of a wave, and so the crest travels faster. And if this continues long enough as the water gets shallower, this becomes the dominant effect, and the crest overtakes the trough and waves break. That's a quick and dirty explanation of wave breaking. Now, here's a section, 50 kilometers long, stretched out of the river between, let's say, Sharpness and Gloucester, and it drops about 10 meters. And here's the tide coming in, a snapshot. The bore is the front of the tide. The high tide is about an hour later downstream. It follows, everything moves this way. And happens is that the river flows backwards for an hour. It's a very surprising phenomenon as the tide comes in, because the water flows upstream, but of course downhill. And that's the picture. So that's the crude, quick understanding of the bore, but we want to understand much more, as I'll describe it in a little while. Most bores are undular. Their characteristic shape is nothing before the bore, then a series of waves downstream. And many, many pictures. Another one. And so this is the phenomenon we want to understand. Now, a little bit of physics, then I'll get back to the bore again after some related phenomena. We want to understand it. The way to understand something that moves is to go along with a frame of reference moving with it. So to try to freeze it, we want to understand a fixed shape. It's not quite fixed, but it almost is. So this is what we want to understand. And down upstream, there's a depth, call it D0. Downstream is a depth, call it D1. Of course, that's greater because the tide is water deeper as it comes in. Okay, and we want to understand this shape as it depends on position as you go down, and also on time, not very much, as we'll see. Here's the physics you need for this, to calculate this profile. The first ingredient is conservation of water. You take a region before the bore and after the bore, and consider the physics in between. You don't need the details just yet. Well, no water is gained or lost. And also, you've got Newton's law of acting on the water, the forces and the acceleration and so on. So that's 2 little bits of physics without needing to know the details in between. And this connects the downflowing river speed and the depth and the upstream, the downflowing is upstream, and the incoming tide, which is downstream, that's depth and its velocity in terms of one number. And that's just the ratio of the two depths. And that ratio, downstream versus upstream, is greater than one, of course. And that's when tidal bores happen. And it's undular if the difference is not too big, and it's turbulent if the difference is bigger. And really, undular bores are much commoner to understand them. Very good. Now, the second ingredient, you have to know about waves on water. And in the language of physics, these are long waves on shallow water. It means the depth. In the deep ocean, the depth doesn't matter. I mean, the waves are independent of the depth. The disturbance doesn't reach the bottom. But when it does, the depth matters. And there's a maximum speed that waves can travel, I've mentioned already. It depends on gravity, of course. These are gravity waves. And it's the square root of the depth. Okay. Now, the first result from this is that upstream, that's ahead of the bore, the flow speed is faster than the minimum wave speed. So waves can't travel upstream away from the bore. The flow is too fast. Downstream, the speed is less, so waves can travel both ways. And these give the waves that you see. Now, that means that the front of the bore is a kind of horizon. It separates regions where waves can and can't travel upstream. Now, that's analogous to horizons in relativity. You've heard of black holes and black hole horizons. The common feature is waves associated with horizons. Now, this isn't a black hole horizon, it's a white hole horizon. That's the analogy, because upstream, away from the front, is, quotes, into the hole. Waves can't travel, but they can come out of the hole. And then they travel through the front and downstream, and then anything can happen. They can go forwards and backwards. So that's a nice analogy between bore physics and a totally different kind of physics to do with black holes, except that it's time-reversed black holes, it's white holes. Now, the third ingredient, it's the only one more we need, is that the speed of water waves depends on the wavelength. Yes, long waves have the greatest speed, I've talked about that, but then short waves travel more slowly. This is the group velocity in technical terms. Now, from that comes a theory, and I've used this phrase P2C2E, which I've stolen from Salman Rushdie's fairy story, and it means processes too complicated to explain. No, because it's a lot of mathematics. We love this kind of thing, but it's not suitable for today. But then you get a result. And the result is a universal shape of the bore, which depends on just one quantity. What is that quantity? Well, x is the distance we want to the downstream. D0 is the depth of the water before the bore arrives. And this big D is a big number. It's the distance traveled from the start of the bore, way downstream, long way. Now, this is a very large number. And this, usually, if your bore traveled 10 kilometers on a river of depth 2 meters, this ratio is about 5,000. So this is the inverse of a very large number, which is important in the mathematics and not today. But that's the quantity that the bore depends on. In terms of this quantity, you've got a universal shape. That's what it is. Now, so here's the, before the bore arrives, here's the tide depth downstream, which is higher, and here are the waves in between. Now, you can get a lot out of this theory. The first consequence is, what about this big D? But what it means is that the bore waves slowly expand as they travel, as the bore travels upstream. It's not very significant, and I can illustrate it. The bore starts, roughly speaking, at Or. I was on the other side, on the Forester Dean side. And then one place you look at it is, you can see it at Stonebench, or you can see it at Maysmore. It takes 1.75 hours to reach Stone Bench. It takes 2.17 hours to reach Maysmore. And this expansion between here and here is only about 7%, so it's not important. But still, strictly speaking, it gently does expand. That's the first thing you get. Second thing is you calculate the depth at the front of the bore. It rises and begins to turn over. You can calculate that. You can calculate the slope. It's usually a few degrees. It looks as if it's much more, but it isn't. Usually a few degrees. They'll call it the wavelength. It's the distance between the first two crests. They get closer and closer as you go further into the bore. The amplitude, that's the height distance between the first crest and the first trough. You can calculate that. And you can calculate the steepness, which is the ratio of those two things. Now, this is theoretical physics. And it's very natural to ask, does it agree with experiment? And here I have to say something which is very important in principle. You probably know that physics is the most precise science. You know, you can predict an eclipse to a fraction of a second. In elementary particle physics, you can calculate the magnetic moment of the muon to 9 decimal places, and it agrees with experiment. Fantastic. This is a different kind of theoretical physics because, you know, there are many confounding features. The river is not straight. Its depth is not constant. Its width is not constant. There's sediment on the bottom. All kinds of confounding factors. So you will never get a theory giving a precise agreement at each place between theory and experiment. It's a different kind of physics, and there's a name for it. What I've described is a minimal model, and the minimal model is this. It's a theory that most economically caricatures the essential physics. Now, if you live next to the bore, you want to know details that this won't tell you. But that's different from what is the basic physics that underlies it, and I've given you the ideas for that. Okay, now some related phenomena before I get back to lore of the bore. Okay, so this is the theory. Here's his observation, and you can stretch, and you can see it does conform. Now, there's an anti-bore. See, if you have very, very, very shallow water, a few millimeters, surface tension is important, and then the physics is different. Still, the square root of the depth is the speed, but it's now the minimum speed, not the maximum. And you see that. Here's your sink, and here's a ring of wave of water that's pouring down, keeping it at a distance. If you didn't keep pouring water in, it would move this way down the plug hole. And here you see the ripples are ahead of the wave, not behind the wave. It's the opposite. You can see this if you've had heavy rain and you live on a slope and look at the pavement, you see groups of waves down the pavement, and each of these groups of waves, a few millimeter or centimeter deep, each of these groups of waves have little waves in the front of them, not the back. So that's the opposite of what happens with the bore. Now something else. This is an illustration of connections in physics. Now, we love connections. They're very important. Charles Frank, my late colleague in Bristol, physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things. Very deep, beautiful statement. And it's not often pointed out, but every physicist, we sort of know it in our bones, and we're always delighted when we find connections between apparently different areas of physics. So it is with this shape. Here's the shape again, and you can think of it as a kind of focusing in space-time. I don't want to go into the details of why that's so, but you can. Now, there are other kinds of focusing where the same mathematics helps, and you can see it. So, for example, this is the shape, actually the slope of it. It's a wave discovered by Airy in 1838, a mathematical shape, describing waves associated with focal curves. They're called caustics. And here's his shape, mathematical terms, the bore is the integral of this, for those who know that language of that sect. Well, you can see it. You can see it in rainbows. That's sunlight focused by raindrops. Now, sometimes you can see in rainbows a number of wave maxima and minima. Usually you can't, because the raindrops are all different sizes and that blurs out these undulations. It's a deep concept, actually. It's called decoherence and has other applications in physics. But when the raindrops are nearly all the same size, and that depends on meteorology, you can see a few of these interference fringes, which really are a direct indication of the fact that light is waves. So the usual rainbow theory, going back to Descartes and Newton, just assumes light being rays, which bend and refract and reflect and according to known laws. But here you see, magnified in the sky, the wave nature of light. Here's another example. Swimming objects have this V shape behind them, decorated with oscillations. Kelvin's ship waves. Whoops, help, tangling up. It's almost independent of the size of the object and the speed, not quite, but almost. It's an angle. So what it is, here it is. This V shape actually is a caustic of the rays of the water waves. That language doesn't matter. It always has the same angle, 19 degrees 28 minutes. That comes from the physics of waves on water. And if you think this is abstract, consider the following. Imagine you're in a little boat here and a big ship passes by. Eventually, its V shape will reach you. You wait longer than you think because you see the velocity of the waves, these little waves in here, and but in fact, the group moves at half the speed. So you wait longer. But anyway, it does reach you, and in your little boat, you rock up and down. You're feeling in your body this mathematical function that I just showed you a picture of. So it's not abstract at all. It's very direct. Okay, so this is a little example of the ubiquity of this shape that the bore exemplifies. Now, the bore is a phenomenon of the incoming tide. There's also a very beautiful phenomenon of the flood tide. That's the horizontal motion of the tide. That's a maximum between the high and low tide, the horizontal flow. And this happens in Scotland, the flood tide counterpart, in the Gulf of Corryvreckan. Now, the Gulf of Corryvreckan is between Jura and Scarborough in the Inner Hebrides. And here it is, the Gulf, and here it is magnified. And here it is, and magnifying again, here's Scarborough, here's Jura. Down here is Barn Hill, where George Orwell lived in the 1940s and where he wrote 1984. Here is the Corryvreckan. The tidal stream is very fast, up to 4 meters a second, and you get huge standing waves and whirlpools. George Orwell was with his young son, not very knowledgeable about the tides, and came to grief, actually, almost capsized. He was sailing with his young son. He narrowly managed to get to the shore where he was rescued with his young son. And why does that happen? Well, I haven't seen a proper theory of it, but it's to do with the fact that the depth varies enormously in this gulf, and it's an interaction between the waves on the water, the tide that flows, and the topography of the bottom. You get huge standing waves. The world's third largest whirlpools. Here it is. Huge. They can be 10 meters high, these waves. You can hear them thundering from miles away. It happens at times when there are high tides, just like the bore. Here we are, and here we are again, and here. Now, I've been several times to see this. Monica came with me a few years ago. Of course, you're advised, if you're a sailor, never try navigating this gulf yourself. But there are a few boatmen who do know what they're doing, and they run tours. So we embarked on one of these tours and arrived at the place, the harbour on the mainland where the boat leaves, and noticed there are two boats. The other one had a TV crew who were making a documentary about waves in general, including the Bore. And there was an elderly guy there who obviously knew quite a bit about the Bore. And I got chatting with him, and I said, "You realise it's quite dangerous?" I said, "Do you know that George Orwell, nearly came to grief with his son?" He said, "Yes, yes, I know." And I suddenly looked at him. I said, "Are you George Orwell's son?" He said, "Yes." It was a really unexpected encounter. We had a nice correspondence after that. He's a couple of years younger than me. Now, every year I buy the tide tables from Victoria Arrowsmith Brown, whose family have been producing tide tables of the Bristol Channel for navigational purposes for nearly 200 years. And they used to be rather large company of printers in some of my first scientific papers were published by Arrowsmith, printed by Arrowsmith, not published. But now it's the only thing they do is this: they buy data from the Admiralty, and she composes the tides. Now, this is how you predict the bores. You see, the bore takes place higher than the navigable places that the tide tables describe. But this is what you do. You see, here's a typical page, a typical month, March 2019. I'm zoom in. Sharpness is the highest point that the tide tables describe the tides for, high and low tides. And the bore is upstream from there. But still, the rule is this: if the tide sharpness is more than 9 meters, see, the tides, just tell you, near Bristol, the tides, the second highest tides in the world, the tide range near Avonmouth can be 17 meters, and it's a huge range. But if the tides of sharpness are greater than 9 meters, and here, this particular month, there are a few of them, then you know there'll be a bore. And if it's bigger than 10 meters, there'll be a big bore. And the one that we'll see in a few weeks on the 30th is the 10.3 at sharpness. Of course, that doesn't mean the bore is 10.3 meters high, although I have seen online accounts that naively say, "Oh, the bore will be 10 meters high." It won't be, of course, and possibly 1 meter, but still very dramatic. And then from this, you can predict when the bore will reach various locations. So, for example, Minsterworth, the bore will reach Minsterworth at approximately the same time as high tide in sharpness, and varying on either side of that in a predictable fashion. You can't predict exactly when it's going to come. It's not like an eclipse. The reason is, depends on winds in the Atlantic, it depends on how much rain there has been, and so on. So the times predicted that you can see on my website or on other websites are really the earliest time, because you don't want to miss it. You sometimes have to go and wait half an hour, and people of little faith think, "Is this ever going to come?" But it does, always. But sometimes it's underwhelming. And when it is underwhelming in the sense that the wave isn't very big, something else is still very dramatic, which is that the river reverses direction. We like to go at night. There's always enough light at night, even when the bore follows a full moon or a new moon. There's always enough light and to see it. And it's not dramatic. You hear it for physics reasons. You hear sounds differently at night from the day. That's another piece of physics. So you hear it coming in the distance. And first of all, you think you hear it, and then, no, it's cars on the A48, or it's a train on the A4. But then eventually it's unmistakable, and you hear it before you see it, and then it slowly comes towards you at about 10, 15 miles an hour, which, by the way, means that you can see it in several places. You can go to one place and then drive and see it in the next, and so on. sometimes if you choose a time when it's not one of the highest tides, you can still see a rather dramatic tide, but you're sort of the only people there. We were there once. In Minsterworth, you can stand by the church and just look out. And then a vehicle approached from behind, and two huge men got out, festooned with aerials and goggles and whatever. It turns out they were Elver policemen, because the River Severn is a place where elvers are born, and the eels come from the Sargasso Sea and they come back to their original birthplace. How they do that is wonderfully mysterious. And elves are protected, and there's an illegal trade, a criminal trade, and they were investigating whether we were illegal elven fishermen. And probably they had been telephoned by people on the other side who'd seen us, their counterpart. And then we had a good conversation with them. Anyway, there's a nice book by Anthony Collat. He's a French surfer. He goes around the world surfing bores, and he has a book of beautiful pictures, including a list of times when the bore arrives compared with when it's at Minsterworth, which is high tide in Sharpness. So there's lots of lovely pictures. In the Amazon, on a tributary of the Amazon near Belém, there's a big bore called the Pororoca. By the way, I travel every year before the pandemic, and now starting to advise on an institute in Natal, which is here. You think it's relatively close. First of all, it's never the right time, and secondly, it's rather difficult to get to the place where the bore is. 15 hours on a boat and so on. But anyway, it's quite an impressive bore. It's a wave. Here it is again. In India, on the Hooghly, there's the Barn. It's a distributary of the Ganges near Calcutta. Here it is. There are two districts coming together, and down they flow. Here again, that's where the tidal bore is, of the tide coming in from the Bay of Bengal. Here it is again. I've got a video here which I stole from the web, and I hope it may be terribly noisy, but bear with me. Oh, I can't hear anything. Doesn't matter. You don't need to hear it. It's a horrible noise anyway. Well, before it was deafening when I tried. I don't know what you've done. Never mind. Here it is. You see it coming, and what you would hear would be just a horrible noise. But don't worry, you won't be deafened. Here it approaches. This is the bore on the Hooghly, the Barn as it's called. Here it approaches. You see it coming in. It's really mucky, lots of mud on the side. And, you will see these gentlemen who are impressed with it in a moment. There it's gone by. So it's quite an impressive sight. When I saw it, it wasn't really impressive. And I think that the guy who I persuaded to take he didn't really know, but we went on the wrong side. It was busier on the other side. Anyway, there it is. Lots of literature about it. I think that's a fanciful picture. Nevertheless, it is one. But I want to read you something. The bore commences at Hooghly Point, the place where the river first contracts itself. And it's perceptible above Hooghly town, and so quick is its motion that it hardly employs 4 hours in travelling from one to the other, though its distance is nearly 70 miles. At Calcutta, it sometimes occasions an instantaneous rise of 6 feet, and both here and at every other part of its track, the boats on its approach immediately quit the shore and make for safety in the middle of the river. In the channels between the islands at the mouth of the Meghna, the height of the bore is said to exceed 12 feet, and so terrific is its appearance and so dangerous in its consequences that no boat will venture to pass at spring tide. And even when I saw it, which was just a little surge, all the boats had gone to the middle of the river, and you saw them twist a bit as the little bore went by. Now, I read you this because of what follows. The Hooghly Bore, as fearsome as it could be, is but a ripple compared to the Cirencester Bore, the greatest of tidal bores. Between the river and the city walls, which are a mile distant, dense suburbs extend several miles along the banks. As the hour of flood tide approach, and he means high tide, crowds gather in the streets, running at right angles with the Cirencester, but at a safe distance. Now, I went to see this some years ago, and here it is. I mean, here's Asia, and here's where it happens, zooming in. Here's Shanghai. You can go from Shanghai, and I shall be there in a few weeks, but I won't have time to see. I don't know if there won't be a bore then. It's the wrong time of year. And here's Hangzhou, beautiful city, very, I keep getting entangled. Well, and the bore takes place here. Now, to give you a scale, here's where the river opens out, and that's about 40 kilometers, in the middle of which is a hotel where we stayed. Beautiful hotel in the middle. Now, compare that with a few kilometers by Avonmouth, let's say, where the Severn bridges are, and here's 40 kilometers. Our river, where the bore occurs upstream, is a few tens of meters in the width between the banks. It's about maybe 50 meters at most. Here, it's several kilometers. So it's a different phenomenon. It's not that the bore is enormously high, but it's just that the scale of it is vast. Now, when we went, it was the biggest bore of the year because that was how it was timed for us. We saw it 6 times, morning and evening, morning and evening, morning and evening. And we were, I think, the only non-Chinese people of the 120,000 visiting there. President Xi has spoken about it. It has, of course, an ancient history. It's an entertainment. You get these guys, mythical dressed guys walking along, and policemen, because some silly people have jumped in and you get drowned, because it can be quite dangerous. There can be an undertow as for a little while the bore is flowing upstream and the bit of the river is still flowing down. So people were killed some years before. So you're prevented from doing that. So here we are, lots of people, and here's the bore coming by, and here it is. It's a turbulent bore, this one. And I'll just show you, again, without the sound. We don't need to know the sound, the bore coming. Now, I want you to notice something. It's approaching. This will go out of shot, but actually the bore comes up to about there, or the tide does, once the river, as the bore comes in, just to give you a picture for it. So here we are. There's a great entertainment. We're sitting in a little cafe just above, so we had a perfect view of it. Here it comes. And you get very excited. Of course, they've all got their smartphones, taking pictures of it. It's gone out of shot now. It comes by. And the quite impressive thing is the distance across the several kilometers across to the other side. So here it comes. And a great roar goes up from the crowds, which you're not hearing. Here it comes by. There we are. Now, this gives you an idea of the scale, because look, here are the people up there. And here's the bore. And you see how they arrange for the boats to be safely away when the bore comes by. And here you can just see, it's terribly turned, but you can see a few of the first few waves of this sort of standard shape. Now, something I saw there which I hardly saw before, which is this. Here's a little bit of the topography, and the bore is coming in. And most of it passes straight down the river, but some of it hits the shore. And, well, when a wave hits something, it gets reflected. We have seen many years ago in Maysmore, when the bore comes by, a few hundred meters out of sight is the weir. We saw a tiny little ripple coming backwards at about half an hour later, a quarter of an hour later. But this is much more impressive. You see here we are. Here I'm looking at the bore approaching safely on the riverbank. And here you see the reflected bore receding. It interferes with its own reflection and recedes. It's a very lovely thing. So that's that. France. Just to say, in Britain, we've got 16 rivers that have bores. Nowhere else in the world has so many. In the United States, there are none. There's one in northern Canada, not on the highest tide in the world is in the Bay of Fundy. That tide up some of the rivers on the Bay of Fundy, the Chapacodiac River, that's right, we saw it, that has a bore, that's Canada. And in Mexico, there's one on the Colorado River that flows down when it's in Mexico, but not the US. And I think the reason is that the rivers are so vast that the tide can't make any headway coming in. So this effect of the tide coming in a gently narrowing river doesn't happen. And I haven't seen a proper explanation of that, but there are none, I've checked. Anyway, France, there was a famous one on the Seine for the same reason as on the Severn. You've got the Atlantic tides in the unobstructed Atlantic coming in. And there used to be a famous bore at Caudebec called Le Mascaret, that's the French name. It doesn't exist anymore, or hardly does, because they dredged the river for navigational purposes, and that spoiled it. But if you drive there, there's Bar Le Mascaret, in which you see nice photographs, old photographs of the bore coming in, people watching it, and there. Now, this actually is the first bore I'd heard of, because when I was at school, I was fascinated by astronomy, and in a second-hand bookshop, I bought what later I discovered is, well, this is a fanciful picture. What later I discovered was actually a rather famous 19th century, and then translated into English in 1907, book on astronomy by Flammarion and Gore was translated. And there I was fascinated to read a description of the bore, and it's something I kept in my mind. I never dreamed I would come to a place, Bristol, where I would ever actually see such a thing. But I want to read what they say about it. One day, after being present at Caudebec, after this always curious spectacle of the bore on the Seine, I returned on foot, where I was overtaken by a countryman with whom I entered into conversation. On my asking him what he thought, and what the old people of his family thought of the phenomenon which they'd observed for so many years, I do not know, he replied, how the wise men explain it, but for us it seemed to be nothing else than the well-known antipathy between salt water and fresh. They are not of the same character, you see, but this is certain, that the fresh water falling into the sea worries the salt water, which it finds a difficulty in mixing. Well then, the salt water ends by becoming angry. It accumulates its anger, and every evening, especially at equinoxes, when it's already naturally furious, it resolves on hunting the fresh water, sending it back with great velocity. I assure you, sir, that this reason is much simpler than the attraction of the moon. Now, I'm not quoting this in any mocking spirit of superiority, because, you know, these people, they didn't know physics, and it took how many millennia for in the evolution of humanity to understand universal gravitation and the fact that the moon can have this kind of effect. So it's very natural that you make theories on the basis of other things that you know in this spirit of connections. And this anthropomorphic notion of water getting angry and not liking salt water and so on is not, even though it's wrong, it's very natural. Also in this book, there's a mythological interpretation. The Seine, nymph of Ceres and daughter of Bacchus, walking one day on the seashore, was seen by Neptune, old monarch of the waters, who, delighted with her charms, set out to follow her. He'd already reached her when Bacchus and Ceres, invoked by the nymph and being unable otherwise to save her, metamorphosed her into an azure river, which ever since has borne her name and has everywhere on its banks joy and fertility. Neptune, however, has not ceased to love her, although she has preserved her aversion to him. Twice a day he pursues her with great bellowings, and each time the Seine escapes into the meadows and goes back towards a source contrary to the natural course of rivers. Sexual harassment is nothing new. Well, once again, you see a natural phenomenon and you want to understand it in terms of other things that you know or think you know, but it's very natural. Now, my last slide, why is it that theoretical physicists is mesmerized by this phenomenon? Well, there are lots of reasons. I've already talked about connection in different kinds of physics and how it's an interesting and non-trivial exercise in applied mathematics to get this shape, get to the heart of it. But there's something else. You see, a certain type of fundamental physics tries to find a theoretical framework into which every phenomenon would fit, however deep you have to go. Well, that's called unification. Nowadays, the aim is to unify gravity with the other forces in physics. Some decades ago, the electromagnetic forces were unified with some of the weak nuclear forces. Very good. The unification that has had most effect on humanity was Maxwell in the 19th century, who understood that electricity, magnetism, and light are all part of a single phenomenon. A huge number of aspects of our technological civilization followed from that insight by Maxwell. But we tend to forget that the first unification was in the 17th century by Isaac Newton. And he understood that gravity, it's the same gravity that pulls us down, holds the Earth in its orbit and the moon, and pulls the tides, which is an amazing thing. I mean, a huge moment in the history of humanity when that was understood. And when you see the bore, all three of these come together. You're standing on the riverbank, the tide is coming in, and it's caused by the moon in its orbit. It's Newtonian physics, the apotheosis of Newtonian physics. He never saw the ball. He never saw a tide. He never went to the sea, but still he understood. So that's the fundamental physics that gets illustrated when you stand and when you see the ball, this beautiful phenomenon. So enough, that's what I wanted to say. And thank you very much for your attention.
Well, thank you very much for that fascinating introduction. I'm sure we've got some questions. Should we start with anybody like to start a question?
Yeah, first, I want to say two things. Yep. First of all, there are no stupid questions. Second is, I don't hear very well, so I might ask John to.
That's assuming I also.
No, you've got a very loud voice.
I do.
You don't have loud ears, it depends. So there is. Yeah.
Sorry, somebody over there?
Yes. So where is the best place to watch the ball, the Severn ball?
Yeah, we used to go to a place called Weir Green, which is on the south side near Stonehenge. But unfortunately, it was beautiful because you could drive down the lane, you could park your car, there was a space there, and you could see it directly. But it's all overgrown now. I did write to the water authorities about it, and they said, well, it's owned by local people, and they have no responsibility to cut the trees and bushes. And their only responsibility is to make sure that the embankment of the Severn Way is intact. So that's the well. There are a lot of places. We tend to go to Minsterworth on the other side. It's just off the A48 there, by Minsterworth Church. You can park just down a little lane and walk a few meters, and then you get a nice view of it as it comes. Then another good place is Over Bridge by on the A40 as it crosses just up north of Gloucester. The only problem with that is it's not easy to park, but if you can find a place on the side, you can walk up and you can see Telford's. It's on Telford's Bridge, and then there's a more modern rail bridge just beyond, and then you get a nice view of it. But the place we really like is Maysmore, which is where the bore almost ends, because you can stand on the road bridge. It's free, and you can park in a number of different places nearby, and you can watch it. And you watch it coming in, and then as you see it under the bridge, you run across the road, being careful not to be run over. You run over, and then you see it receding on the other side, and it's very dramatic. So these are the places we go. When we went exploring that region during the day, there's a pub there, the White Hart, and we tried to have lunch there. And the publicans didn't look like familiar publicans. The reason is that they're Gurkhas, and in the evening it's a Nepalese restaurant. So if the timing is right, you can have a nice Nepalese dinner and then go and watch the ball. It depends on the timing. So these are the places where we go, but there are lots of other places. Well, okay, the River Severn, as it approaches Gloucester, splits into two channels. There's the main channel I've described. The other channel goes round, break through Gloucester and then back again, and beyond Maysmore it joins again. If you stand at the junction, lower parting, you get there by one way, you walk for about 20 minutes from Over Bridge, there's a path. Then you can see the bore approaching, you can see it splitting, it goes along the two channels. The main one I've described, and then a substantial bore goes along the other. That's very beautiful. You do that during the day, you wouldn't do it at night because it's kind of slightly awkward to walk along the path, but so they're the places I go, but we go, but it never fails. It can be disappointing, but then as I've said, you see the backwards flowing, which is the river starts off rather gentle and smooth. Often it depends on the weather, but often it's perfectly mirror smooth, and you see reflections of the trees on the other side. But once it passes, it's completely, after the main waves have passed, it's completely turbulent, wild back rushing. And you see logs and things which are gently floated downstream come rushing back. It's very dramatic. And it flows backwards for about an hour until the high tide arrives, and then it gently subsides.
Any other questions on that? I'm going to ask you one,
yes,
which is quite ridiculous, but given that the moon is supposed to be moving away from Earth at about 2.5 or 3 centimeters a year, if one went back to the Severn, say about 10,000 years ago, what literally the layout was probably slightly different, but would it?
Well, I mean, I think I'm not sure, because I don't know how long the Severn has existed. I don't know. I mean, you know that Britain, the British Isles have been joined to the mainland and not joined to the mainland, and how that's affected the Severn, probably dramatically. So, other things being equal, the bore would have been much bigger then, but whether things were equal, I don't know. The most dramatic effect of the moon receding is that there'll be a last total eclipse of the sun, because it's a coincidence that now the moon is almost the same angular size as the sun. So when the moon covers the sun, which mostly it doesn't because they move in different planes, it doesn't happen every new moon. When it covers the sun, the main light is blotted out. You see the sun's atmosphere, the corona, very beautiful thing. But that's an accident of the epoch in which we live. And if you wait 500 million years, put it in your diary, there'll be, because the moon is going farther away because of tidal friction and conservation of angular momentum, then there'll be a last total. It will be too small to cover the sun. And that's probably before the sun becomes a red giant and explodes.
About halfway to our final
That's right.
conversation.
Exactly. So that's a predictable effect of the moon. You know, with on the tides, it depends on the geography and the topography of the Severn. I mean, it may be known, but I don't know what it was.
No, I just, yes,
Well, just a point from geology is that river estuaries tend to be a phenomenon at times of falling sea level,
Yes.
when water is getting locked up in ice.
Mm.
Because that's when rivers cut down into the geology. So the quite long period in Earth's history where you just don't see river estuaries really don't exist as we would see them in the Severn. So the Severn, you know, the fact that we have an estuary there is an effect of the ice age.
It's a recent geological.
Relatively recent. And I was told that geologically speaking, over the stretch of the estuaries are actually quite rare.
But that's interesting.
Geological phenomena.
Okay, so that means that tidal bores are quite rare as
Yeah.
well. And these are timescales much shorter than the long timescale of the moon significantly being closer to us. Yeah, that's thousands of millions of years or hundreds of millions of years, whereas you're talking about a few tens of thousands or hundreds. Yeah.
yeah. No, it's an interesting point, yeah.
Can I just come back so I can hear you?
If it's high rainfall.
Yes.
On the 30th of September, did you say that today?
That's interesting. I learned something recently, which I stupidly hadn't thought about before. I had the naive view, if there's a lot of rain, it tends not to be such a high bore, because you imagine, I'm thinking like these people quoted in that old astronomy book, that the tide has to fight against and you wouldn't get such a high bore, and that the bore would be delayed. But actually it's not. The bore comes earlier when there's a low water level, because the depth is greater and the bore is a wave, and the speed of waves on water is greater. And indeed, we've observed this when we've been to see the bore under conditions of when it's been raining and there's a lot of water in the river. The bore comes closer to the predicted time, not the sort of half an hour you can sometimes wait. So whether it's, I mean, if it's horrible weather on the 30th, also the 29th, and also the 1st of October, in the evening, the big bore, we will still go and see it, even though it's not so pleasant, it's tipping down.
Any other comments or questions?
You haven't mentioned the sound of the bore. I find that when we've watched it, you can hear it long before you actually see it.
Yes, I did mention it, but still, yes, that's why we tend to go at night. You know, at night it's cooler on the ground, so the air is denser, and therefore sound bends down. It refraction towards a denser medium. So at night you hear things that are far away. In the day, you know, you can be in a meadow on a sunny hot day. It's all very quiet, and that's because the sound refracts up away. It's the opposite. So at night you tend, I mean, you can hear it, of course, during the day as well, but it's most dramatic at night. And as you say, there's this wonderful roaring and rushing that approaches. It's part of the experience. There's another reason for going at night. The other reason we go at night is it isn't so contaminated by surfers. No, I'm going to say this clearly. Of course, it's a wonderful thing. And you saw the surfers are rather small, but boats can tend to spoil it, but surfers don't. And there are many more boats in the daytime than in the night. So we tend to go at night. But if there is a big bore in the day, it's certainly worth seeing. Yeah.
Sorry, did you have a question?
A comment more than a question.
Yes, please.
I was interested in your explanation of the tidal bore off Jura, because I think I've seen a similar phenomena between mainland and Hoy in the Orkney Islands.
Interesting. Yes, there's another big rushing channel.
Yes.
Yes, well, there may be. I don't know that, but I don't doubt it. But the Gulf of Corrib Reckon is the one that the Admiralty warn you against sailing if you're
Yeah.
innocent, or even quite an experienced. I see. So what's that? I mean, you also see great waves at certain
You
times.
see almost like a step in the
Yeah,
water.
exactly.
Sometimes there's a little break on it, but and you see that the ferry sort of falls over it.
Yes. Well, this happened on our tour boat when we went to the Gulf of Corrie Record. We went straight in. You see it in this rushing region of water. So all of a sudden you're in a boat. Of course, everything is safe. You've got the proper safety gear and all that.
Yeah.
But still, you feel it all of a sudden.
Yes.
And what the boatman did, you saw the whirlpool, gently steered us into the whirlpool, and you gently go round and round in this boat, a period of a few seconds, and round and round you go. You don't get sucked down, of course. That's Edgar Allan Poe's mythical tale, but still very impressive. And then you go out again. So I don't know if you have the same thing in Hoy. I mean, a big ferry probably wouldn't be vulnerable to that. These are smaller boats.
Yeah. The ferry didn't seem to be bothered. He just went over it.
Well, obviously used to it. Very interesting. Thank you.
Yeah, that was what you didn't tell us about. When you went to see this phenomenon,
Yeah.
what you after you talked to the Sun.
Well,
you never mentioned exactly what-
no, they went off on their
Yeah.
boat, and we went on our boat, and I didn't see them. But I did write to him because there are various other interesting tidal features there. And so we had a brief correspondence. He is, as you might imagine, the president or director of the Orwell Foundation.
Yes.
Yeah. So very interesting. Yeah, he's a retired engineer who lived down south, but he apparently owns some property up near there.
Right.
And whether it's I guess he was about 3, so he might just remember this experience.
Yeah.
Trauma. Whether it's a sort of act of dealing with the trauma that makes him probably not. He seems a thoroughly well-grounded person. But, anyway, so yes, so I've seen him since.
Sorry, one more. Yeah, I'd like to ask, can a bore be reproduced artificially in a laboratory at a terribly small scale? Like
Yeah, to some extent, yeah, there are some experiments in they're rather difficult experiments but there are people have made measurements and so on. So you do, I mean, basically you see the waves traveling upstream. I wouldn't call them experiments of the kind where I can really test the theory quantitatively. It's very hard to reproduce the exact features. But yes, you can. Yeah. Yeah, it'll give you a couple of meters high. And but the hard part is getting the long travel distance where this shape, one thing I didn't say, comes out of the mathematics. It's a very nice thing. But the bore starts somewhere, and how it starts is kind of random. But the mathematics tells you that however it starts, it soon forgets those details and becomes this wave that you see. Now, the ones made in the laboratory don't go anything like the distance you would need to see the emergence of this sort of stable mathematical shape. You see something like it, but it's never, you never see the fully evolved shape. But there are, yes, in Bordeaux, there's a guy, I can't remember his name, it doesn't matter. It's an artificial channel makes measurements. Yeah.
Well, if there are no more questions, we'd like to thank you very much for a fascinating discussion of the movement of water, and some of it very close to home, which makes it even more interesting. Thank you very much indeed, Professor Byrne, for coming this evening all the way from Bristol and telling us about your experiences. Thank you very much.